Welcome everybody. So today we are going to see another problem. Already we have seen three problems. The first two problems were with simple supports. The extreme ends are simple supports. Continuous beam with extreme ends simple supports. The third problem was continuous beam, a two-span continuous beam fixed at one extreme end and simply supported at another extreme end. So this is our fourth problem. Our fourth problem is evaluate the bending moment and shear force and deflection of the beam for the given figure. So our given diagram is we have a fixed beam. So this is a fixed continuous beam fixed at the exterior supports A and B. So exterior supports A and B are fixed support. We will take this as C. So exterior supports are fixed supports and the intermediate support B is simple support. Now this is subjected to a UDL of 2 kilonewton per meter over the span AB, and at the mid of the span BC we have a 12 kilonewton concentrated load. The span length AB is 6 meter and the span length BC is also 6 meter, and this 12 kilonewton load is acting at the center of the span, acting at the mid span. So we will take this point as D, and the span DC is therefore this will be 3 meter. Now we will move on to our problem. Okay, so our step 1 is always, our step 1 will be to draw the simple beam moment diagram. Simple beam moment diagram, also known as our mu diagram. Okay, simple beam moment diagram. So here we have two spans AB and BC. So we will assume both the spans AB and BC are simple supports. So we have AB is a simple support, simple supported beam, and BC is another simple supported beam. Now the loading on AB is 2 kilonewton per meter, and on BC at the center we have a 12 kilonewton load. Now the span length is 6 meter for AB, and for BC also it is a 6 meter, and this DC is 3 meter. Now we will draw the simple beam moment diagram. So we are assuming the ends are simple supports, so that when it is subjected to a UDL, our bending moment diagram will be a parabola. So this will be a parabola, and the maximum moment will be at the midspan, and the maximum moment will be equal to m max is equal to, it is WL square by 8. So we get 2 into L square is 6 square divided by 8. We get 9 kilonewton meter. So here it is 9 kilonewton meter. Now for the span BC, since it is a concentrated load at D we will have the maximum bending moment for this span, and this bending moment, the diagram will be like this. Okay, so this is B and this is C. This is the center of the span. So this you can use MD is equal to, you can use either W AB by L, or you can use W L by 4. Okay, So here in this formula, A is also, this is A, BD is A and DC is B. So A is 3 meter, B is also 3 meter. Or you can use WL by 4. So L is 6 meter, 6 by 4. So we get W is 12 kilonewton into L is 6 divided by 4. We get 18 kilonewton meter. So this magnitude is 18 kilonewton meter. Now we will draw the simple beam moment diagram. So our simple beam moment diagram is, this is a parabola and this is a triangle. Here it is 9 kilonewton meter and this magnitude is 18 kilonewton meter. This is called simple beam moment diagram. And this diagram is always positive. That means it is a sagging, the bending moment, the deflection is sagging. Therefore, we have sagging bending moment, right? Now, so once we have determined the simple beam moment diagram, we have to determine area into x bar, that is distance of centroid. Now, so the centroid will lie, for the span AB, the centroid will lie at the center. Similarly, for the span BC also, since it is an equilateral triangle, BD is 3, DC is 3. This is 18 kilonewton. So this B, D and this is, these are equilateral, this is an equilateral triangle. Sorry, not equilateral triangle, the two sides are. Two sides will be equal, this BD is equal to DC. So both are similar triangles. So for this triangle, also the centroid will lie at the center. Either you can take the whole triangle together or you can split this triangle into two as we did in the previous problems. So now for this span AB, our area into x bar will be equal to, since it is a parabola, the area is 2 by 3 into base is 6, height is 9, multiplied by, see when you take from A or when you take from B, since it is at the center, the distance is 3. So we get 108. Similarly, for the span BC, our area into x bar will be equal to, it is an equilateral triangle. Sorry, it is a triangle. So it is, you can take half into base into height. So half into base is 6 into height is 18. And since the centroid lies at the mid span, it is 3. You can use this, or as in the previous problem, you can take area of the triangle, this first triangle multiplied by the distance from B, distance of the centroid from B, plus area of the second triangle multiplied by the distance of the centroid from B. Okay, now, so this is equal to 162. Okay, so the next step, so this is our step 2. Our step 3 is we have to determine the unknowns. How many number of unknowns are there? So in this problem, the unknowns are, we have a moment at A, we have a moment at B, we have a moment at C. Because A and C are fixed supports, moments are not equal to 0 at A and not equal to 0 at the C. So we have moments at A and C. So that means we have three unknowns. We need three equations, three moment equations to solve our problems, to find the answer. So in order to that, see, this is a fixed support. So to the left of the left support, that is A is fixed. So to the left of A, we will take an imaginary span or a zero span A dash A. This is a zero span with zero loading conditions. Similarly, since C is also fixed support, we will assume another span, another imaginary span C dash. Okay, now our first set of equation is by considering the span A dash A, AB, you will get one equation. Then the second set of span is AB, BC, we will get second equation. The third set of span is BC, CC dash, we will get third equation. So solving the three equations, we will get the three unknowns, the moments. So now our unknowns are MA, moment at A is unknown, moment at B is unknown, and moment at C is unknown. So totally three unknowns. So now we will move on to step 4. Our step 4 is we will apply the theorem of three moments. So in order to apply the theorem of three moments, the first case we will consider the span A dash A and AB. Consider the span A dash A and AB. See, this is A dash A and AB. So A dash A is an imaginary span. AB is a 6 meter span with 2 kilonewton per meter loadings. So this A dash A means this is an imaginary span. So A dash A, imaginary span L is equal to 0. And for AB, it is of span length 6 meter and we have a UDL of 2 kilonewton per meter. Now we will apply the theorem of three moments. We know the theorem of three moments. Equation for the theorem of three moments is M A dash into L naught by I plus 2 times MA, that is the intermediate support. Here intermediate support is A into L naught by I plus L1 by I plus MB into L1 by I is equal to minus 6 into A naught X naught bar, because see, naught represents the imaginary span. So A naught X naught bar divided by I naught L naught plus A1 X1 bar by I L1 plus 6 into E delta A dash by L naught plus E delta B by, that is the first support and the last support, third support, first support and third support by L2. So, see, this term becomes 0. This becomes 0 because this is an imaginary span. Here, so we have 2MA into this L naught becomes 0. Everywhere I gets cancelled. So we get 2 MA into L1. L1 is 6 meter plus MB into L1 is 6 is equal to minus 6 into, this is an imaginary span, so 0. A1 x1 bar by L1. So here A1 x1 is AB. So for AB, for the span AB, our AX bar is 108. So this is minus 6 into 108 divided by L1 is 6. So we get 12 MA plus 6 MB is equal to minus 108. This is our equation number 1. Now we will consider case 2, that is considering the span AB, BC. Okay, so we know AB, BC. So A, B, C, 6 meter, 6 meter. AB is 2 kilonewton per meter. It consists a uniformly distributed load. And in BC, we have a concentrated load of 12 kilonewton at the midspan. So here there is a 12 kilonewton at the midspan. Now we will apply the theorem of 3 moments. So here the theorem of 3 moments is MA into L1 by I1. See, I1 is I here because there is no change in I throughout the span or throughout the beam, plus 2 times the intermediate support, that is MB into L1 by I1 plus L2 by I2 plus MC, third support is C, MC into L2 by I2 is equal to minus 6 into A1 x1 bar by I1 L1 plus A2 x2 bar by I2 L2 plus 6 into E delta. The first support is A. So E delta A by L1 plus third last support is C. So E delta C by L2. So substituting the values we get, see we can cancel all the I, all I gets cancelled because I1 is equal to I2 is equal to this property I, moment of inertia, is the same throughout the section. Because no variation is given in the problem, we will assume it as the same. So we have MA into L1 is 6 plus 2 times MB into L1 is 6 plus L2 is 6 plus MC into L2 is 6 is equal to minus 6 into, here A1 x1 bar is for span AB, A2 x2 bar is for span BC. So we have already calculated that for AB, for the span AB, AX bar is 108. For span BC, AX bar is 162. So 108 by L1 is 6 plus 162 by L2 is 6. And here there is no deflection, there is no settlement of support, so that becomes 0. So we get from this we get 6 MA plus 24 MB plus 6 MC is equal to 270. This is our equation number 2. So we have one more case, that will be our case 3. So case 3 is, we will be considering the span BC dash. This CC dash is an imaginary span. So we have BC, this is BC, and CC dash will be an imaginary span. L is equal to 0. Here BC is 6 meter, and in BC we have a 12 kilonewton load at the center of BC, at the mid of the span BC. Now we will apply the equation of 3 moments. So equation of 3 moments here is MB, that is first support, into, we will take this as L1. L1 by I1 plus 2 times the intermediate support MC into L1 by I1 plus the second is the imaginary span, so L0 by I0 plus MC dash, that is the third support, imaginary support, MC dash into L0 by I0 is equal to minus 6 into A1 x1 bar by I1 L1 plus A0 x0 bar by I2 I0 L0 plus 6 into E delta A by L1, sorry, it is delta B, the first support is delta B plus E delta C dash by L0. So from this we can remove all the I. All the I get cancelled because everywhere there is I. See, this term becomes 0, that is why our I is getting cancelled. So MB, L1 is 6, we get 6 MB plus 2 times MC into L1 plus L0 is 0, it is an imaginary span, so L1 is 6 plus this MC dash is an imaginary span, this becomes 0, so equal to minus 6 into, so this term becomes 0, imaginary term, A1 x1 bar by L1. So here A1 x1 bar is for the span BC. So we know for span BC, AX bar is 162. So it is minus 6 into 162 divided by L1 is 6. So from this we get 6 MB plus 12 MC is equal to minus 162. This is our equation number 3. So now we got 3 equations. So solving these 3 equations, we get the value for MA is equal to minus 5.25 kilonewton meter, MB is equal to minus 7.5 kilonewton meter, and MC is equal to minus 9.75 kilonewton meter. That means, see, at every supports we have negative bending moments. At every supports we have negative bending moments. Now we can draw the bending moment and deflection diagram. So let us draw the bending moment and deflection diagram. Okay. So first of all we will draw the fixing moment diagram. So plus our fixing moment diagram, that is at A, this is A, B and C. So MA is minus 5.25. So it is 5.25 kilonewton meter. MB is 7.5. So greater than this, 7.5 kilonewton meter. and MC is 9.75, minus 9.75, greater than this, okay? 9.75 kilonewton meter. So we will draw the bending moment diagram. It is at A 5.25, at B it is 7.5, at C it is 9.75. So this is called, this is everywhere negative. So this bending moment diagram is called fixing moment diagram. Fixing moment diagram, because this bending moment is due to the fixed support. Now the final bending moment diagram for the given beam will be the addition of simple beam moment diagram and fixing bending moment diagram. So simple beam moment diagram, the moment is positive everywhere. Fixing moment diagram, the bending moment is negative. So combining both, we will get, so we will combine the both. So for AB, it is a parabola, 9 kilonewton meter. For BC, it is a triangle, 18 kilonewton meter. At A, we have a negative moment of, use another color. We have a negative moment of 5.25 kilonewton meter. And here we have a negative moment of, below this, okay, 7.5 kilonewton meter. And at C we have a moment of 9.75 kilonewton meter. Now this is negative. See, at these supports, at all these supports, we have negative bending moment. All these supports we have, at these supports we have negative bending moment, and at the remaining portions of the beam we will have positive bending moment. So this is positive. This bending moment is positive bending moment. Okay, now, so this is called bending moment diagram. Now we will draw the deflection diagram. So how will we draw the deflection diagram? So at this portion, up to this portion, we have a hogging, bending moment. So at this portion becomes a 0, deflection becomes a 0, and up to this we will have a sagging deflection, okay, and at the support we will have again hogging up to this point, and after that up to this point we will have a sagging, and after that we will have a hogging. So this is the deflection diagram. Now our aim is to find the shear force diagram. So how will we find the shear force diagram? We have to determine the reactions. Reactions at A, reactions at B, and reaction at C. So how will we find that? Now we will take the moments to the left of C. Anywhere you can take. Taking the moments to the left of C, taking the moments to the right of B, etc., etc. So what we get is, we will draw once again. So this is A, B, C. In the span AB, we have 2 kilonewton per meter. In the span BC, we have 12 kilonewton concentrated load. Span length is 6 meter, 3 meter, 3 meter. Now, this point is D. Now our moments are at A, we have a moment of 5.25 kilonewton meter. This is negative. See, when you are taking any section on the beam AB, when you take any section on the beam AB, the left of the beam, the anti-clockwise becomes negative. So this 5.25 is negative bending moment. That is why it is the moment is drawn in this direction. Now at the point B, the moment is 7.5 kilonewton meter. That is, when you are considering any section on the span AB, the right clockwise becomes negative. So the direction is like this. This is for the span BC. So anywhere on the span BC, this becomes the left anti-clockwise becomes negative. So it is minus 7. This means it is minus 7.5 kilonewton meter. Same way on the span at the support C, our direction of bending moment is like this. So it is 9.75 kilonewton meter clockwise. Now we will take the moments to the left of C. We will consider the moments to the left of C. So considering the moment to the left of C, what we get is, it is RA into 12. This RA into 12. That is, left clockwise is positive. See, before that, our reactions are reactions at A, we have reaction at B, and we will have reaction at C. Our aim is to find these things. So it is RA into 12 plus RB into 6 minus 12 into 3 minus 2 into 6 into 3 plus 6 and minus 5.25 is equal to minus 9.75. See, I will repeat. We will give some space for drawing the bending shear force diagram here. So, considering taking the moments to the left of C, okay, we are taking the moments to the left of C. What we get is RA into 12. This is, so we are considering the moment to the left of C. So to the left of C, RA into 12, that is positive. Okay, that is left clockwise is positive. Now we have a moment here, that is 5.25. That is left anti-clockwise, negative, minus 5.25. Now we have a load of now we have a load of 2 kilonewton per meter. So it is anti-clockwise, so negative. Minus 2 into 6. Two into 6 multiplied by the distance, that is 3 plus 6, 9. Now we have another moment plus 7.5 minus 7.5. So this becomes 0. This becomes cancelled. Now we have RB, that is positive. So plus RB into 6. Now there is a 12 kilonewton load. So minus 12 into 3 anti-clockwise. Again this 9.75 is clockwise. So it is plus 9.75 is equal to 0. So from this we will get an equation in terms of RA and RB. So this will be our equation. We will take our equation as 4 because we have 3 unknowns, right? Now we will take the moment to the right of B. So this is B. When taking the moments to the right of B, we get this RC into 6. That will be positive. RC into 6. Now this minus MC minus 12 into 3 okay, where will we write it? Right. Okay, we will write one by one. This will be our one equation. Now we will take the moments, taking the moments to the right of B. Taking the moments to the right of B. Okay. We have here we have an anti-clockwise. So right anti-clockwise becomes positive. So 7.5. So we are taking this right anti-clockwise becomes positive. So 7.5. Now this 12 right clockwise becomes negative. So 12 into 3. So minus 12 into 3. Now we have a right clockwise, again negative, that is minus 9.75. So minus 9.75. Now this right anti-clockwise becomes negative. Sorry, right anti-clockwise becomes positive. So RC into 6 plus RC into 6 is equal to 0. Okay. So from this we get 7.5 minus 12 into 3 is 36 minus 9.75 plus 6RC is equal to 0. We get 6RC is equal to, this is 7.5. We will calculate. So 7.5 minus 36 minus 9.75 is minus 38.25. So we get 38.25. So from which we get RC is equal to 38.25 divided by 6. We get 6.375 kilonewton. So this is RC. Now the unknowns are RA and RB. So for the next step, finding RA and RB, we will consider the moment to the right of A, or we will consider the moment to the left of B. Okay? So we will consider the moment to the left of B. So taking the moments to the left of B. So when taking the moments to the left of B, we have, this is a clockwise moment. So left clockwise is positive. So this is 7.5. So we have 7.5 Now there is a 2 kilonewton per meter. So left anti-clockwise is negative. So 2 into 6 into 3 minus 2 into 6 into 3. Minus 2 into 6 into 3. Minus 2 into 6 into 3. Now we have a left anti-clockwise. So left anti-clockwise is negative. Minus 5.25 kilonewton meter. Minus 5.25. So minus 5.25. Now we have RA into 6. Clockwise is positive. Left clockwise is positive. So RA into B. RA into 6 plus RA into 6 is equal to 0. So totally 1, 2, 3, 4. Let us check 1, 2, 3 and 4. Okay. So what we get is 7.5 minus 2 3s are 6 6 are 36 minus 5.25 plus 6 times RA is equal to 0. So we get 6 RA is equal to, let us calculate, 7.5 minus 36 minus 5.25 is minus 33.75. So that is equal to 33.75, which implies our RA is equal to 33.75 divided by 6. We get 5.625 kilonewton. So RA is 5.625 kilonewton. Now we know upward loads is equal to downward reactions, right? So our RA plus RB plus RC is equal to, so total loads is 2 into 6 plus 12. 2 into 6 plus 12. So 12 plus 12, 24 kilonewton. So we have already found RC as RC is 6.375. 6.375. RA is 5.625. So plus RB is equal to 24, from which we get RB is equal to, RB is 24 minus 6.375 minus 5.625, we get 12 kilonewton. So RB is 12 kilonewton. Now we can draw the shear force diagram. So now 6.375, RC is 6.375. RC is 6.375 kilonewton. RA is 5.625. 5.625 kilonewton and RB is 12 kilonewton. Now we can draw the shear force diagram. So our shear force diagram is, so at A we have a load of 5.625 kilonewton. Now we have a UDL of 2 kilonewton per meter. So total loads is 2 into 6 is 12. So we have a linearly varying section. So this is 5.625 minus 6 into 2 is 12. We get minus 6.375. So here it is minus 6.375. So you put a linearly varying line, and from here we have a vertical reaction. RB is 12 kilonewton. So it is minus 6.375 plus 12. We get 5.625. This is 5.625. So after that, from up to D, we don't have any load. And at D, we have another 12 kilonewton load. So it is 5.625 minus 12. We get minus 6.375. So from D to C, we don't have any loads. And at C, we have the reaction as 6.375. So it is 6.375 minus 6.375, we get 0. So this is positive, here it is positive, and the remaining portion it is negative. Here it is negative shear force. So that means from A to this point, we have a positive shear force. Now up to B, from this point to B, we have a negative shear force. And at B, from B to D, we have a positive shear force. And from D to C, we have a negative shear force. So we have analyzed our problem. Hope you all understood. See, we will repeat once again, just a revision. Okay. We have first step, we have drawn the simple beam moment diagram. Then our aim is to draw the fixing moment diagram. For that, we are using theorem of three moments. Since the ends are fixed support, we are assuming some imaginary span to the left of A and to the right of A. We are adding both, we get the bending moment diagram. So after drawing the bending moment diagram, we can draw the deflection diagram. After that, after marking all the moments, we can find using static equilibrium conditions, find the reactions at A, B and C, and you can draw the shear force diagram. So hope you all understood. Thanks for listening. Thank you.